Okay, so hi all. Thanks so much for joining us for the first Pratt Research Talk of the year. I'm Rachel Asher, the Associate Director for the Office of Research and Strategic Partnerships. Our office's mission is to foster new and exciting research opportunities for faculty, staff, and centers at Pratt, and to help you make connections with each other and also with industry and community partners outside of the Institute. One way that we're doing this is by providing a platform for research active faculty to talk about their work and to inspire you to think about what might be possible in your own research at Pratt. In addition to our conversation with Rebeccah today, I'd encourage all of you to check out our upcoming talks with Jared Delane on November 18th and Amanda Hahn on December 9th, both at 12:30 p.m. Please check out the links in the chat, or you can go to prattresearch.org and scroll down through our landing page to read about their talks and to register to attend. We're in the process of scheduling research talks for the spring semester, so if you're interested in presenting or know someone who would be great for the series, please reach out to us at research-partnership@pratt.edu. Our office is here to support you. If you have an idea germinating, have a project that you're ready to get started on, or even have a funder in mind, please feel free to contact our office. The best way to reach us is again at that email address in the chat, research-partnership@pratt.edu. Today, we're talking to Rebeccah Pailes-Friedman, professor, industrial designer, co-founding partner in SEArch LLC, and founder of Interwoven Design Group, LLC. She's also going to be the moderator of some of our future research conversations this fall. A pioneering researcher in space architecture, wearable technology, smart materials and design methodologies, Rebeccah contributed to numerous publications and has lectured globally. She's the author of Smart Textiles for Designers, Inventing the Future of Fabrics, released in 2016 by Laurence King Publishers, London, and is currently working with a team contributing to NASA's Artemis program, which will land the first woman and the next man on the moon by 2024. Today, she's talking to us about Project Olympus. Space exploration architecture introduces a design approach to a lunar landing pad. We'll start with a presentation from Rebeccah, followed by a conversation. So please get your questions and comments ready for her. Rebeccah, over to you.
Hey, thank you for having me. I'm going to encourage everybody to use the chat. So as I'm presenting, if thoughts or questions pop into your mind, use the chat, and then we'll use the chat to be able to guide a Q&A at the end of the presentation. So I'm going to start by sharing my screen. Share screen. Okay, there you go. Okay, I do this for a living, so as we all do. Let me know when you can see the presentation.
We can see it.
Okay, great, excellent. Okay, so I teach in industrial design. I'm an industrial designer, but I'm also a partner in an architecture firm. I am the sole industrial designer in a sea of architects. But it's good because the skills that I bring to the team really make a difference in the type of design solutions that we come up with. So the name of the architecture firm that I belong to is SEArch Plus, which is Space Exploration Architecture. So there we go, a little delay on the slides. So this is us. We are primarily a women-owned business. We have our token male member, Michael Morris, who teaches in the architecture school. And other than that, there's 5 women that, that drive the design of this firm. This has been really one of the key aspects of what we see as the future in both aerospace and the built environment. It also gets us in the door at a lot of places, because finding a primarily female-led design team in the aerospace industry is really still unique, although my personal feeling is it shouldn't be unique, but it is. So what do? This is like our little symbol that stands for Earth for Space and Space for Earth. What we do is we develop human supporting design concepts for living in space and on Earth. We think that there's this strong correlation between the research that we do for living in outer space and how it can affect the way we live on Earth. So I put these symbols together to sort of show what some of our present research is and some of the collaborations and spin-offs that we've been able to derive from the work that we've done. So where does space technology meet Earth development goals? And a lot of it is around construction technology, because we focus on large-scale 3D printing. There's also a lot of material innovations that come with how are we going to turn, like basically it's called regolith, but it's like either Mars dirt or moon dirt. How are we going to turn that into a material that we can then 3D print? We also are really interested in sustainable operations. It's really critical, especially in space. It's really critical to understand sustainability, because we have to bring everything with us, and we have to try to reuse everything that we possibly can, so that we can have one, we can survive in the space environment, but two, we can stay there as long as what we're hoping to be able to stay there, which would be what we're hoping is years. And then finally, Technopole. So that's like mashing together all these people in all these different technology areas and trying to come up with really like sort of groundbreaking innovations in a very short period of time, because you have this mashup of technology. So how did we get started? A number of years ago, when SEArch first came together, we entered this Centennial Challenges. NASA put together this competition called the Centennial Challenge 3D Printed Habitat. It was a multi-year, multi-phase design competition. Well, it was 50-50, design and construction. So there'd be a design phase and a construction phase, design phase, construction phase, back and forth, where one would inform the other. And twice we won first place in design with Mars Icehouse, and once we won fourth place in the 60% design for Mars Xhouse. So those are our winning submissions on the side of the slide. And here's some of our additional work. Now, the first thing that we got major acclaim for was Mars Icehouse, which was 3D printing ice on the surface of Mars. But then after we won the competition, some people at NASA were upset because they hadn't defined what we had to 3D print. And since we printed in ice and won, they weren't too happy, because really what they wanted us to print in regolith. So then they changed the rules. And that meant that we had to redesign our entire project. So we designed Mars Xhouse 1, which is in the top center there. But what we don't know a lot about printing with regolith, and we didn't know if we could print a pressurized structure. And we also don't know the long-term effects of how the regolith would affect the human body. So what we proposed was an inflatable center with a printed shell for radiation and ballistics protection. That earned us a fourth place because they said they didn't want an inflatable. We kept breaking the rules. That's what happens when you're a good designer. You're always breaking the rules, right? So then they told us only pressurized habitat built completely out of regolith. And then we did Mars Xhouse, which is on the left-hand side, the second picture down, and we won first place for design on that. And then from these conceptual projects, the research that was generated actually drove us to some industry projects. So here's a little bit more and a couple more renders of Icehouse, where you can see one of the things that we really liked about Icehouse is that we introduced this, and we still to this day use this, a mechanical core that has all the life support systems and mechanics inside it that we would bring from Earth, and then we would print around it. Icehouse has an interior structure that's pressurized, and then it has an exterior like shell that gives us like a semi-pressurized environment, almost like a garage, where astronauts could survive, but they wouldn't have to have all of their huge EVA equipment on. That, just so you know, that EVA suit is like 500 pounds. So it's really difficult to maneuver for a long period of time in an EVA. And the research that came out of this was, well, how do you 3D print ice? And we did a number of experiments, and we were able to actually 3D print our model in ice. And our idea was to use swarm robotics to be printing, and then as the ice evaporated, they would continue to print on the habitat. So that project actually led us to a project with, like, this is an ongoing process with NASA Langley called Mars Ice Home. Now, this one is like water ice filled bags that are made into this igloo shape. And this is actually we went from like theoretical, you can do this, to an actual like paid contract on how could you use water ice as a radiation protecting shield and build a habitat with Langley. And then again, there were a lot of the elements that we had used in Ice House. We applied in here, like the green wall and growing space. And then we did a lot of radiation and ray tracing studies to figure out like the thickness of the ice to really protect the astronauts when they were, in the habitat on the Martian surface. We also were approached by UTC Aerospace Systems to rethink this. So that thing, it looks sort of like a high school gym locker. That's really, they call it a pallet, and you store all of the machinery and equipment and supplies inside of these things. But with all the different public-private partnerships, the sizes of the rockets are all different diameters. And but the ECLS people wanted to be able to, ECLS is life support, but the life support manufacturers wanted to have a way to flexibly place these elements inside any type of rocket, whether it was a tiny one or a big one. One of the innovations that we came up with, this was one of my babies because this is more industrial design than architecture, was I figured out how to change the front panel geometry. You can see that it undulates, that's so that it handles sound better, but also it tapers, and that allows it to be translated through the hatch and gain 22% more interior space than the other one. So it was an efficiency thing. Also, it made it like a lot nicer to navigate the space. Here again, we went back to Mars X House version 1 and Mars X House version 2. And this shows you how from Ice House, we still looked at incorporating that central core into the architecture so that we knew that the life support and other MEP systems would work inside whatever structure we were building. So I remember I told you it was a design phase and a construction phase. So each time we had a construction phase, we had to prove something else with our 3D printing. This was a smoke test where we had to prove that if we printed this, they gave us the file. We didn't design that thing, but once we printed it with our technology, that it would hold water and it would hold smoke. This was like proof of concept. What were we going to be able to make a pressurized habitat? And then this is the final design for Mars X House. But now we're going to go to the moon, and now it's real. Mars is a dream and it's going to happen in the future, but the moon is happening now. We're looking at having a lunar outpost on the moon by 2028 with initial launches as soon as 2025. That's 5 years. That's like an undergraduate architectural education, and we're going to be having people on the moon. So what did we do? So I'm going to tell you some specifics and some generalities. So the first thing is ISRU, which is in situ resources. So that means moon dirt or regolith. And we had to look at how we would actually do surface construction with ISRU materials. We set out these like pragmatic principles that we thought were really important that affected performance, safety, and cost for construction on the lunar surface, and they were adaptability. So the physical conditions are really horrific, like the temperature swings, zero gravity, no atmosphere. It's really a challenge. So we had to make a proposals for buildings and infrastructure that were highly adaptable. Flexibility, we needed to be able to to apply these the flexibility to these changing requirements, because NASA still doesn't know exactly where we're going to land. So, you know, usually in architecture, you know your site, you study it, you know where the sun's going to go, you know what the land looks like, and then you start designing. We had to design something that could be adapted to wherever NASA decides they're going to land in the future. We don't know yet. I mean, there'll be more design once they decide, but for our work right now, it had to be flexible. We needed it to be resilient. We had to make sure that no matter what, that it had to accommodate failure, because we know it's going to fail at some point somehow, and we wanted to be able to create a design that was resilient. And then, because it costs so much to bring things up to space, we had to really think about multi-use, like commonalities. Could we use the same thing for multiple tasks, etc.? So this is the dream of where they think we're going to take the surface site infrastructure. So we'll start with like roads, berms, landing pads, and just planar surfaces. Then we're going to progress to habitats, and those type of habitats that we first progress to will end up most likely being like utility shelters or for primary radiation shielding. We also have to simultaneously develop the technology to be able to achieve these. So we have to look at excavation and site preparation. We have to look at the materials, ISRU production. How are we going to use that? Then we have to think of all the different landing systems that are going to land on the moon, because there's many different types of landing systems. And then how are we going to produce the propellant for multiple landings and takeoffs? And finally, what are the power sources and what is the form of the power generation going to look like on the surface? I'm keeping this talk super high level, but that said, if I say anything that's confusing, please raise your hand and let me know. I'm happy to like talk about anything. But I talk about this stuff a lot. So my husband says I sound really, really smart, like I know what I'm talking about. And I'm like, yeah, but there's people that know so much more than me. But this is where we're at. So we thought, realistically, if you were going to build on the moon, the first phase you were going to have to do, and your initial construction focus was going to have to be on critical infrastructure. So, you know, you have to protect the equipment that you're building or bringing from ballistics, right? So things that travel really fast and puncture the surface of things or corrode the surface of things. There are moonquakes. They're kind of like earthquakes, but they last days, not just hours or minutes. So we had to protect for that. And then we had to also think about how are we going to get on and off the surface of the moon. The next phase is, the phase 2 was going to be to establish infrastructure in place. So construction is going to begin. We're going to start thinking about the initial habitat. The third phase is going to be the master planning of the actual lunar base. What is that going to look like? How are we going to make multiple buildings? What are their purposes going to be? And then finally, strategic expansion. So how can we design something that could be strategically expanded over the course of time? So this is a little GIF that shows like the surface construction process and an ideation, like how we would capture the regolith, how we would transport the regolith to the printer, how we would dump it and then start printing and creating a horizontal surface. You can see in the far distance over there on the top right, might not be the first thing that you see. You can see the gantry style printer that's starting to print the blast wall on a landing pad. So these are material handling, excavation, planar surface, and then the gantry construction. So some of the things that we started out when we started working on this project. So just to put this into some context, we started this project at about the time classes ended at the end of May, and we just finished it up last week. So this is about 4.5 months worth of work. So we looked at what do we need for planar construction. The first thing we thought of is there is no gravel. There aren't big rocks on the moon. So maybe we would use the 3D printer to print random gravel or interlocking pavers or piles that we could like either sink in or protrude up from the surface to create some planar surface construction, some foundational work. Then we looked at shielding. We thought of this idea of 3D printing, sort of, we call them jacks, like how you toss jacks, but large scale. Could we print like multiples of shapes and then pile them up and use them as berms or areas for blast walls to protect the habitats once we started building them? And then finally, we started looking at habitats and utility shelters and different ways you can build. So in 3D printing, we have this problem where you can't do more than a 30-degree angle of overhang. So how are we going to overcome creating an enclosed structure when we couldn't do more than a 30-degree overhang? And we looked at lots of different ways of doing that, with modular units, with printing flat and stacking, all sorts of different ways we looked at that. Now, I wanted to talk a little bit about the surface site infrastructure and master planning. This example that I'm going to show you is an example of how we use research in our practice. And we haven't published this yet, but we plan on publishing this paper. So we took available data maps from NASA that showed like numerical temperature data, numerical slope and topography data, and numerical illuminance data. And then we made a digital model that superimposed them to generate what we thought were optimal sites. Now, remember I told you NASA doesn't know where we're going to land, right? So what we did is we developed this methodology, a framework, so that no matter where NASA decides to land, we could apply this framework and then narrow down the most optimal sites that had like the best slope, the least temperature swing, and the most sunlight, or whatever we wanted, to be able to determine where in their, like, you know, whatever crater they decide they want to land at, where's the best place for us to build a habitat. This, to me, is like really sort of a groundbreaking way of looking at numerical data and applying it to a design principle. So we looked at also, when we were looking at our master planning criteria, on top of the data and analytics, we looked at where other projects, moon-based project, had decided to land. And then we did like sort of a compare and contrast between existing work and where we thought would be optimal sites. That's why in this top right corner, the white ones are other people's ideas, including Norman Foster's ideas, and the red are where we thought our primary areas were. And one of the things that we did was we looked at how could we follow like topographical lines to place roadways, and what would be the most efficient way we could plan not just a single habitat or a landing pad, but like that phase 3 where it could expand exponentially. How could we use like our methodology to figure out where would be the best place to place things for expansion? And then we applied some zoning principles, like some basic zoning principles. We're big on schematics. We draw a lot of schematics. So that we could understand the relationship between the different things, like the habitat, the landing pad, the greenhouse, where we were going to harvest the materials, et cetera, et cetera. So I know I'm jumping around quite a bit. There's a ton of information. I could probably talk for about 4 hours, but I'm just trying to like grasp some of the things that I think are interesting about how we would design something and how we use the research component to inform our design. The part of this project that I'm really like my hands got the most dirty on was development of the landing pads. So one thing about designing lunar landing pads, and also Martian landing pads when we get there, is that we don't want a scene like this. when a lander comes down to the surface of the moon and it launches the lunar dust, it's called the ejecta. When it launches the ejecta, those little pieces of dust are razor sharp and they literally sandblast everything in sight. And our super expensive and very difficult to get to the surface of the moon machinery is not going to survive if it gets blasted with this type of dust. So we know that the first thing we're going to have to do is to build a landing pad. So how do we go about figuring out how to build this landing pad? This is the official NASA rendering of our first landing pad. We were about 50% done with the design. One of the things we had to talk about was the sizes of the landing pads and the different types of landers it would accommodate, and how do you get to and from the landing pad. So we developed this sort of typology for the landing pad where we would have these different parts. We'd have the central pad where it would be a harder surface. We have an external ring where it might be a less hard, maybe like that printed gravel surface. Then we have a dust ring to collect the dust. And then we have the blast wall to hold the dust in. On the right-hand side, you see some of the very early schematics of some of our thought processes on how to enter the pad, and like some sort of different types of ways the wall could we thought about not just containing the dust like inside a wall, but deflecting the dust or slowing the dust down. Like maybe we can't keep it all from escaping, but we could slow it down. These were all different ways that we thought about designing the pad. Then the other thing that we had to look at was the options, the size options. So we know right now we need a bigger pad because of what the technology that exists. But we are saying that as we get better at developing landing technology, the size of our pad can decrease. This is good because it's more sustainable. We can print it faster, and we could have more of them. So you could have more things coming and going at the same time, rather than just one thing, and then you have to wait for it to take off before the next thing can come. So this is a scale drawing of a section view of the 3 different landers that NASA is considering using: the Blue Moon lander, the Starship from SpaceX, and the Dynetics lander. So each one of those is drawn to scale. Now you start to see why, like, the size of the landing pad is such a point of contention and a design opportunity. So when we initiated this project to design the landing pad, we consulted with a number of amazing, really amazing subject matter experts. And one is Phil Metzger, who teaches at the University of Miami. And his entire body of work consists of understanding the plume ejecta on landing and launch. And what his work, we read a bunch of papers by him. That's the turbulence effects graph on the right-hand side. But the biggest takeaway for us was the majority of the dust plume could be contained in a 17-degree angle. So how can we design something that's going to contain the ejecta in a 17-degree angle and then deflect it down into a dust trench? This was like the schematics and the paper that we worked on we really thought about how we could apply this to our physical design. So when we looked at our strategies for mitigating dust, I touched on this a second ago. We looked at 3 things. How can we absorb it? So maybe we could stack the jacks all up and there would be cavities between the jacks and the dust would go in and get trapped and it would be absorbed. How could we deviate the dust? So maybe it doesn't travel so far, because, you know, dust can travel so far that it can leave the orbit of the moon and it can travel infinitely into space, and it could damage You know, it could damage a lot of things, like all of the satellites that are now circling the Earth. So we really looked at how could we deviate the dust, maybe slow it down, or like just keep it lower. And then finally, how could we accumulate the dust? And we were dreaming up, maybe we would even have a landing pad Roomba, like a robot that like goes around on the pad and like vacuums up the dust after each landing or launch. So we came up with a couple of different solutions. This one is my favorite solution. We thought about we were inspired by a sunflower, and we created this like vaulted scheme of the sunflowers with 3 entrance points. And the entrance points, what we realized, this was one of my babies, when I was like, okay, we have a landing pad, but like the astronauts arrived, where's their car? Like no one was thinking about it. They were just designing landing pads. The car was all the way over here. So then we figured, oh, we need a place to park the car. So when they get out of the lander, they jump in the car and they can travel to the habitat, right? I know, sounds stupid. It's really simple. No one had thought about it. So we thought of adding these like arched entryways, and we thought, well, not only could we park the lander in there, but we could also leave other types of equipment or refueling or repair or other types of things, like, you know, our landing pad Roomba could be stored in these tunnels. Also, when the printer goes in and prints all these arches, we can fold the printer up like a jackknife, and then it can travel outside of the tunnel to print the next one. So this sort of shows you the construction sequence for the sunflower vault scheme. And this is it from above. And you can see we still use that same typology with the center pad, with the interlocking pavers, a looser construction, maybe a printed gravel or something like that for the outer pad. And then to save printing time, we decided to print the vaults and the wavy roof like with a thinner layer of regolith, but then to berm up loose regolith around the outside for both strength, so it can be a full-fledged blast wall, but also for any sort of radiation protection. So if something should happen and the backup plan is that the astronauts have to go into the rover for an extended period of time before they can take off, they could actually live inside the rover, inside the tunnel, and have radiation protection. So this is a section view, and you can see we've sort of put all of our different ideas together with a little dust trench on the side and the vaults to collect all the dust. And this shows that no matter what size of the rover, we've covered our 17-degree angle. So it's a successful design in that it matches up to Phil Metzger's work. Now, that said, none of this has been built. None of it has been tested. I have dreams of printing it to scale and testing it with baby powder and compressed air and seeing if it really works. But they have to renew our contract before I put in any more hours. And then here, this is the final rendering of our sunflower vault landing pad on the moon. So this helps you imagine what it would actually look like at the end of construction. And that brings me to the end of my brief talk and the beginning of our Q&A. And I would really welcome anybody to jump in a conversation and let me know, let me pick my brain. Let me tell you anything you want to know about constructing on the moon, and I will tell you everything I know, which I'm going to tell you is a microcosm of what a lot of people know. Hey, Mark. I didn't see you before. How you doing?
Hi. Amazing, amazing work. And I'm really familiar now from this semester's work with NASA and Michael about what a challenge it is. And I'm seeing how amazing that design is relative to the depth of that challenge. So I'm super impressed.
Thank you. It's been a lot of fun.
Yes, yay.
It's been a lot of fun, and I think it's also really
no,
interesting. Yeah, go ahead, Allison.
No, I was just going to say that before we get into your questions, I hate Zoom talks because we don't actually just like clap, you know, after you're done. So if you unmute yourself for a second and just clap, you know, yay. All right.
Thank you.
Anyway, I just to introduce myself, I'm Allison Druin, Associate Provost for Research and Strategic Partnerships, and I am so thrilled, Rebeccah, with what you've shared with us. I've known you for how long? Over 3 years now, and I've never really quite understood all the things you've done, and I still don't, but I think it's just amazing to listen to you share your ideas. Already there's, I have 3 questions in the chat, and Julie, thank you so much for starting the questions as well. Julie, do you want to unmute and ask your question, or do you just want to have Rebeccah read it?
I'll unmute. I was wondering if everyone on the project who was working on it were industrial designers, or if like it was a mix of different disciplines.
I'm the only industrial designer. Everybody else are architects.
Okay.
So it's my job to say, no, you can't make stairs 14 inches tall. I don't care if there's no gravity. Your muscle memory is still going to trip. So, so there's a lot of things. I mean, I think that I came into this with just basically being a space geek. But the other partners are all architects, although one of the partners, since her architecture degree, has gotten a second master's degree in human-computer interaction. And her specialty is really understanding the way that the technology is going to affect the construction.
Gotcha. Thank you.
You're welcome.
So Rebeccah, you want to pick which of my 3 questions you want to answer first?
Okay, I like your second question, because I agree with your first one. It's not really a question.
Right.
It's like, yeah, adaptability, flexibility, resilience, multi-use. Yeah, those are primary drivers for almost anything. You're right, especially when you're talking about sustainability. Your second question, though, is why do you think your research team was so successful at breaking rules? And to be honest with you, I think because we are really pragmatic problem solvers. So we've worked with NASA now going on 8 years, and we know that we're not going to send anybody up to any planet anywhere if it's not safe and they can't come home. That's like the number one thing. It has to be safe. So when you're looking at developing new technologies, and you're also like, so we have these 2 clients, right? We have the one client who's the 3D printer who's like new technology, only printing. And then we have NASA, which is kind of a conservative place. How do you mash the 2 up? And I think that's why we broke so many rules. We kept thinking of the practical application and development along a continuum, rather than just jumping to the end. It's always good to jump to the end or have a vision of the end, but also understanding the steps it takes to get there. That, and I just think it's designers' nature to listen to everything and then sort of like improv and say yes and. So I think that we do that a lot of yes and.
Hey, David Kim, do you want to unmute and ask your questions, or do you want Rebeccah to just answer one of them, or 2 of them, or 3 of them?
Oh, I can unmute. Can you hear me?
Yes.
Yes.
Hi. Great talk. Thank you very much, Rebeccah.
You're welcome.
I had 3 questions, and I don't know if you wanted to answer all of them, but the first one is, how do you test an envelope for Martian or lunar atmospheric conditions? And then did NASA, I'm assuming you probably had a lot of information provided by NASA in the competition briefs or the prompts that were given, but I'm just wondering how extensive that was, and if you had to actually obtain more information from NASA for that. And then how your research has impacted your local, meaning earthly projects.
Okay, so I'm going to start with 2 and then go to 3 and then end with 1. So, so first of all, the one thing about NASA is it is funded by our tax dollars. So literally everything that they know, or like 95% of things that they know, are all available online on the NASA website. If you are a super sleuth, you can find almost anything that you need. So like when we were doing the data analytics with the different maps and superimposing them, all of that is available to the public online. You just have to really look for it, or you have to know somebody and you can ask them, where is it? And they'll show it to you. And a lot of, we read, I'm gonna conservatively tell you, I read 125 academic papers. Yeah, I was not bored in COVID, I'll tell you that. So, and I think that that's really where we get the information. There was no, if we couldn't find the information, it most likely just didn't exist. So if you wanted to do work like that, it's really easy to find that information if you have to just put in the legwork. And then how does this, so you asked us, the first question is, how do you test an envelope for Martian or lunar atmospheric conditions? That's a really good question. We have vacuum, we can do a scale model in a vacuum chamber and test it. We also did, like for the construction sequence on the Centennial Challenge, we did smoke tests and water tests, but really the biggest test, it isn't going to be whether it can hold pressure, because we can do things like post-tension and all sorts of reinforcements to be able to make sure that it can hold, the pressure vessel can hold the pressure. I think the biggest challenge on the lunar surface is going to be the temperature differentials. It's about 300 degrees difference between day and night. And one habitat can be lit by the sun on one side and in the complete darkness on the other side. So we actually roughly calculated that it could be as much as a 6-inch expansion in materials on the same habitat at the same time. That's why we were designing for failure. We did, for our habitat, we were thinking of 2 shells, where the outer shell sort of keeps the inner shell in complete darkness. And that's one way that we can mitigate the temperature swing. So, and in terms of testing, I mean, we can do the best we can on Earth. Like they were just printing a landing pad in the desert this past couple of weeks. So we're gonna print, we'll print it on Earth, and then we'll land and take off on it and see what happens. And then we'll take that into space and do miniature experiments. And then your final question, and this is why the chat is so good, because I can remember all 3 questions, is how do we take this and use it on Earth? And I can tell you that one of our next possible projects that we have lined up is to do an actual full-scale printed version of either X-House or our new lunar lantern design on Earth. We're looking at a site in Milan and we're in discussions with Lend-Lease, the big developer, to be able to actually try to print our habitat to see how it would work. That's one way. The other way is the technologies that we're developing for 3D printing on in outer space are going to be applied to 3D printing on Earth. So already our 3D printing partner, Icon Technologies, they're working to print homeless shelters, and we're now in discussions with with some Indian tribes in the Dakotas to print housing for them using this sort of technology that we're developing for like a self-sufficient freestanding housing for them. So that it goes back and forth. Like we think about what we have to do to be in outer space, but then also that informs how we might apply that on Earth.
Fantastic, thank you.
Welcome.
So Rebecca, Mark would like to ask his question verbally.
Yeah, and I think you actually, Rebecca, just started to address it a little bit, but first I want to apologize. I'm going from meeting to meeting, so I missed the beginning of your presentation. And I'm really regretful about that. So I don't know if these are recorded, but I would love to have an opportunity to go back and see the whole thing. So my question is around scientific process, which traditionally, you hold several things constant and you change a single variable in order to understand how that, how the environment responds to that one shift. In this case, you have to be speculative around a lot of technologies and the technology readiness level of those technologies. And it's a real balance, which might invoke group dynamics. It might invoke the kind of client input from NASA or from ICON. And I wonder if you can tell us a little bit about where you've been willing to really speculate and where you've pulled in, even if it has to be anecdotally, we didn't go there. We're designing for 5 years from now. And maybe you addressed some of this, I apologize if you did. But we're designing for what we think is realistic for 8 years from now. These are the risks we were willing to present, and that's how it was received by our clients, or that's how it worked in the team. I'd love to hear a story about that.
Okay, so we did a lot of that. I mean, you can't take on a project like this without doing that. And I mean, to be completely transparent, we were I felt like we were a little bit in the middle of a tug of war. So NASA was very conservative with their idea of the central core and even an inflatable with a printed regolith radiation and ballistic protection, where our client, who basically was the one that was paying us, their whole trajectory is to develop the technology to 3D print. So they didn't really want to hear, well, it's going to be 50 years before we actually are printing on the moon, right? It's they wanted to say 5 years, we got it, no problem. So there was a lot of that, so we ended up presenting variations of an idea, where one was really speculative, which meant it was an aggressive timeline, and one was much more, I'm going to say realistic, but none of it's really realistic, so everything is unproven. But one was more realistic in that it was a more conservative timeline. And then we would present it in sort of this a spectrum of solutions, so that we wouldn't we wouldn't make one person more upset and the other person tell us we were full of shit. Do you know what I mean? It's so really that was I can tell you about specific things, but I think generally that's what we did, was think about best case scenario for this, worst case scenario, where's the triple redundancy? And how could we live somewhere on that spectrum so that because if we don't do it conservatively, NASA doesn't take us seriously. But if we weren't forward thinking enough, our client would think we weren't doing what they had needed. So the reason why they hired us wasn't to design, infrastructure, to be honest with you. The reason why they hired us is so that we could paint a picture for them of what is possible to build, and then they could develop their technology to build it. It was really smart on their part, right, to employ design so early in an engineering process. They're really a forward-thinking company because they were able to do that. And also, I didn't mention, but they actually hired 2 architectural firms to work side by side. Mark, you probably already know because you work with Michael, but they hired us and they hired Bjarke Ingels. And that was sort of like Davy and Goliath, because we're 3 people and they're 500. But it was really interesting. They sort of gave us the same brief, and we didn't really collaborate in the traditional sense, but we started seeing each other's work when they were at about 90% done and we were at about 50% done, because they started before us. And I think that also shows that, and I think Bjarke Ingels, their solution was only the habitat. They didn't address the landing pads, and theirs was much more speculative than what we were. We've worked with NASA so long that I think we actually had a much more pragmatic approach, if you can even think that autonomously printing in situ materials on the surface of the moon is not speculative. So I hope that answers your question.
Totally, and I'm so glad I asked it. just boiling it down to a kind of spectrum of responses is just the most beautiful little soundbite too, right? Because you kind of have to satisfy so many kind of viewers or engaged, kind of stakeholders in the process. So I really appreciate
Absolutely.
that. Thank you.
You're welcome.
Okay, we probably have one more, time for one more question or one more comment. Any takers?
Me.
Yes,
Anita.
Dean.
Me take. I just want to say it's always a pleasure, Rebecca, to see what you're doing and I think I love the way you describe how you have to think outside of the box to different audiences is probably more succinctly and more broadly than anybody else I know in our school can do that, just to understand, rather than just to sort of practice the craft of my discipline in my own area of expertise, that broad thinking, but yet drill down on specifics, both pragmatic, operational, and conceptual. I think just so much appreciate, and it's a pleasure to see this, what you're doing. So I'm just here to spread affection and gratitude.
Thanks, and it's also really nice to see the faces of so many of my favorite people. It's been so long.
I know.
So I appreciate it. I do a lot of different separate things, and I think now that I'm not a young designer anymore, I'm more comfortable with the fact that I can do these things that on paper just don't seem related, but somehow all make sense to me. And I think that I've been really lucky to find other people that I can collaborate with, and in an environment like Pratt that encourages me to just keep thinking big. So I'm just really happy that I could share some of my wacky summer project. Basically, it was a summer project, right? I started it when classes ended, and I was like, no, classes are starting. We got to finish this up. So that's what I did over the summer.
Great.
Well, thank you so much, Rebecca. I'm going to throw it back to Rachel. And Rachel, will you remind us again of our next few speakers? And we already have registrations for the next few speakers, even in larger numbers. So we're excited about this talk series. Tell your friends to come back and listen to the video, because the video will be available. Rachel.
Yes, so the next talk is going to be on the 18th of November, 12:30, so same time slot, Wednesdays at 12:30, and that's going to be Jared Delane talking about the desegregation think tank, which sounds really exciting. And then in December 9th, also at 12:30, Amanda Hun is going to be talking about two different projects that she's working on, one about participatory research and the other about eating together again. So that's going to be really great too. So you can find all that info at prattresearch.org, or you can go straight to those Eventbrite links that I have at the top here.
Thank you, guys.
Thank you.
Thanks so much.
Enjoy the rest of the day.
Good to see you.
Bye.